Hello and good morning everyone. I am Brij Singh, a PhD student at Department of Geophysical Imaging and Institute of Geophysics, Polish Academy of Sciences. And my research interest in exploring mineral exploration uh, pretty much concentrated all over the Europe. And I am currently working in an European Union Smart Exploration project. And today's topic is the secrets of the subsurface, minerals and ores, which is my current primary research interest. In this presentation, I will let you know that how we will be using this seismic method and how this is applied in the exploration industry of oil, gas, minerals, and in other related research. So I will let you know about that in this presentation. So let's start our presentation. So to begin with, I would like to let you know that what is first that a subsurface, what we are saying here. So subsurface is nothing more than just a layered structure of the earth. So if we look at the cross section of this earth, and we have these different deposited layers which we call it strata or stratum, and if you will see in that we have different layers which is comprising of different materials. So here we can see that it's a gas reservoir, then a confining layer, then we have coals, then saline water. So it just depends of our interest that what we want to explore and what is our depth of exploration. So in our case, when we are talking about the mineral industry, so our research interest lies very, very shallow to very near to the surface. So what we see from our naked eyes is called as regolith. Is the uppermost section of the crust, which we call as the regolith, and soil is a part of the regolith which supports the growth of the plant. And below this regolith, we have our bedrock, which is a lithified soil structure, and it's a permanent structure. So this term, the bedrock, which I said, it will be a bit important, and I will let you know why and why is it important in our case. And so let's talk about a bit about minerals. That what are minerals? So they are mainly um, falls in two categories. First is the rock forming minerals, and the other is the ore forming minerals. So the rock forming are those minerals which are found in abundance in the rock of the crust. So they are found in the Earth's crust, and there are more than 2,000 minerals which were found, but not in a very big quantity, so it makes it less effective or less important for us. And the second category is the ore-forming minerals, which are of the economic value, and they do not occur in abundance in rock. So we have to explore them, we need to hunt for them, and we have to find out where are they, because they are found in very, very concentrated forms and in patches in the earth. So it's not like we are gonna explore and it will be huge deposit, but it's in patches. So we need to have a method which can map these really, really well. So here we can see that we have pretty much defined our minerals into mainly into 6 categories. And here are few of the example of these categories, like quartz, magnetite, hematite, which falls in the mineral group oxides, then feldspar, mica. So here we have just to let you know that is different elements make different mineral groups, and according to the physical and chemical conditions, different minerals were formed. So for an example, only 8 of the elements make 98% of the crust, in which the most abundant and the important ones are oxygen and silica. So they make a huge portion of the earth crust because they form in a tetrahedral form, and they are the most important ones, because our main target of exploration is the very shallow upper crust, not more than that. There is just an example that what we call as a mineral and an ore. So we have just found know about what's the difference in that. And here we have an example of quartz, which is in the when it's in the liquid state is called as the glass, which we are producing for like more than 5,000 years. So glass we all very much know, and this is just a volcanic ore. So it's found in very concentrated form, and we are actually targeting this ore so that when we are going to explore it and mine it, so that it should be in such a quantity that it should be economical viable. We can process it through industry and we have a profit of that. So here is just an example that what's the difference in the oil and gas, and when we say about a mineral. So here is an example on your left about the deepest offshore rigs in the Gulf of Mexico. So here you can see that the oil reservoirs are starting from 3,200 feet to 7,000 feet. So our in some of the basins around the world is even more than that. And on the right side we have the deepest open pit copper mine from USA, and you can see that its depth is 4,000, but is the deepest, not. And the present mining industry have a capacity of exploration, or I would say mining, not more than 600 to 700 meters. So the current existing methods of exploration, like the electromagnetic, the gravity methods, the magnetic methods, they don't have a good resolution to find these minerals more than 300 to 500 meters. So we really need to have a new technique or a method using which we can explore more than 1,000 meters or up to 2 kilometers in depth, so that we can mine them, because the exploration of the mineral deposits all over the world, which are in the very shallow sections, are depleting, and the demand is keep on growing because the population is keep on growing. So we need to investigate our new methods to explore it. Today I will not talk about these gravity methods, the magnetic or the electromagnetic method which I just mentioned, but I will concentrate my topic mainly on the seismic method. So it's a method, a geophysical method of mineral exploration. So I will first let you know what is geophysics at all. So geo, if we just break this word, so geo comes from the geology, which is the study of the rocks. And physics, we know so it combines and says that the physics which is applied to study the properties of the rocks. And in geophysics, we are pretty much studying about the natural processes of the earth. So it includes the investigation of the earthquakes, the exploration of oil, gas, minerals. If we have to look for water reservoirs, so all this comes, these investigations comes under geophysics. So today I will let you know about seismic method. What is it? What is the basic principle? And how we are getting such high resolutions, and why we are able to look into deeper earth with respect to other methods. So here just have a cross section of the earth. You can see that some of the layers which you found in the earth crust. So what we do, that we put a source on the surface, and we put some receivers as well at some distance from this source. I will let you know what is this surface, source, what kind of source we are using, and what are these receivers, and what is the principle we are using. So whenever we are using this source, we are propagating our energy into deeper earth, and this energy gets reflected from this earth and gets received from this into these receivers. And all these receivers, the data was all acquired in a recording vehicle, and we store a continuous record of these signals, and we further process it and build some structures based on these energy which we recorded through this receiver. So I will let you know what is these receivers, was the principle involved, and how exactly we do it, and what's the assumptions behind that, and also the challenges. So here is the source. So we are currently using two types of sources. So one is the dynamite, or I would say explosive sources, and the second is the vibroseis. So what I mean by the explosive source, so by dynamite, so we drill a hole into the ground, maybe 6 feet to 8 or 10 feet, and we put this dynamite, and we have a detonator on the outside, on the surface of the earth, and we give a signal, and this dynamite blasts inside the ground and produces a huge energy which further propagates into the ground and gets received by the receivers. And second is the vibroseis. So in the vibroseis, we have very huge trucks, and in these trucks we have a base plate which is attached to this ground. So it's very much similar to hammering. When we hammer something, so if we have a very big hammer and we just hit the ground or anything else, it breaks it. So when we have this very strong machines, and we thump this ground using this base plate, and we generate some energy which propagates inside the earth and get reflected and received. So why these two different methods were used? It is because when we use the dynamite, they are pretty much strong, and we don't have exactly control on that once we blast it. So if we have an exploration site very near to some habilitation, some houses were there, or some sensitive structures were there, so we are pretty much restricted to use that, because it can damage the permanent structure. So that is why we have this vibroseis as well. We can control this thumping, and we can control the energy, and it gives us some leverage to use it in some sophisticated areas. And so we are currently using these two sources, the dynamite and the vibroseis. So next are the receivers. So what's the basic principle? So we all know about Faraday's laws of induction. So what it says that when we have a permanent magnet, and when it is moved from this coil, a voltage is developed. So this galvanometer in that, and either you move this magnet or you move this coil, and some current or voltage is generated. So using the same principle of the Faraday law of induction, we have developed our receivers, which are called as the geophones. So what the geophone does, it converts this ground motion into the electrical signal. So how it does that, we have a spike which we insert into the ground. So this is the ground surface, and we just put it vertically inside that, and we have this coil which is attached by a spring on that, and we have a permanent magnet. So when the energy comes from below the surface, it moves the ground upside down, and that is why this magnet gets moved while the coil remains the fixed. So it's the same principle used here, and that is why when we are changing this flux, a voltage is developed through that, and we record some signal in this form, and this is a continuous recording which gets recorded in some format which can be used for interpretation and processing in the recording track. So we have a number of receivers attached to each other, and each of this voltage is recorded. So receivers in practice, you can see that they are not very big, and you can see these spikes, and these are connected to each other, and this is how it looks like in real. So these are of different frequency range. It just depends on what kind of exploration you are doing. If you are doing it for very deep, then it will be less frequency, and if it will be very shallow, then you can use high frequency. So here you can see in the vehicles these small geophones into the hands, and we need to carry it and they are all connected to each other. And herein is just another example. You can see that the exploration which we did in 2016 in Finland. So you can just see that we need in a real survey, when we are covering a huge area, then we need a lot many of these receivers. And you can see on the back, these are all geophones, and here as well. Here is an example into the field how we do that. So we put all these receivers into a straight line in a straight line with some fixed distance of one geophone to the other, and it just depends. If we are doing it a two-dimensional survey, then we just put a single line. If we have a three-dimensional survey, then we have parallel lines to this line, and we simultaneously record this signal into all these geophones simultaneously. So now I will tell you about what's the basic principle, how we are using, and what's the concept behind it. So first, what the really simple concept is, all we know from our primary education, that distance is equal to velocity into time. So let's suppose we have our source as this position and our receiver at this position, which always remains fixed. So when we blast or we use our vibro size here, so at the moment we blast the dynamite, we record the time, and so the energy will travel from the surface and it will reach to this receiver, and when the first energy strike to this receiver, we also record the time, that at exactly what time it reached this receiver R. So we know when it started, and we know when when the first strike happened. So we know that the time which this energy took from this point S to point R. So let's say this total distance is X. So for an example, let's say that it's 1,000 meters apart, and it took the time 10 seconds. So I can easily compute the velocity of these layers. So what would be the velocity? Is distance upon the time. So let's say 100 meters per second. So the concept behind this computation of this velocity is that through all these years of research and laboratory investigations, we have laboratory tests that which minerals have what kind of densities, and if I know the density, then I can compute what I can expect the velocity range into these minerals. So that is what we are interested into, computing the velocity of the layers. And if I am able to know the velocity of some layer, then I can indirectly interpret what could be the material in that. And if I can know what is the material, then possibly I can say what minerals exist into this velocity. The second very basic principle what's used is from the Fermat's principle from optics. So what Fermat's principle says, that in the ray of light, when it travels from one point to another point, is always takes the fastest path. Or what it means, that it will always travel through a path which is least resistive. It's also applicable same into the electrical signal. So if we have a current, then it will always follow the shortest path, which has the least resistive, or the least resistive path, or indirectly the fastest path. So it's the law of nature that we always follow the least resistive one. So in this way, in the previous one, I saw you that ray is traveling from this very uppermost layer, but it's also traveling in the vertical direction and at some angle. So according to this Fermat principle, the first energy will strike with the fastest path. And in this configuration, this is the shortest path which is possible geometrically. So earlier we have a simple equation like this, distance is equal to velocity into the time. Now we have some kind of a triangle form, and we need to compute first that what is the distance S to P and P to R, and the time we already know. So we have to know that how much this energy has taken from S to P and then P to R. So, and why this energy is getting reflected is because of the property which is called as acoustic impedance, which is the most important thing in seismic methods, and it is called as is the product of density into the velocity. So the product of density and velocity is called the acoustic impedance. So whenever there is a change in acoustic impedance, we always get a reflection of the energy. So I will let you know why and how. And next, in the another example, in order to compute this this distance S to P and P to R. So what we can do, we can just break it into this hypothetical line we can draw, and we can just divide this offset or the distance S to R by half, and now it's some kind of a right angle triangle. So we can just apply Pythagoras theorem, and using that we can just compute this hypotenuse, and same for this triangle as well. And when we knew this distance S to P and P to R, and we know the time, we can compute the velocity in the same way. So this is how it works and what's the basic principle behind that. So let's suppose in the second part with the same principle, let's put that we have n number of receivers and we have a source, so we just blast it or use the Weber size. So we have energy propagating into the earth, and now we can see that we have a different velocity of these mediums. So what I mean by here, the velocity, that these layers, individual layers, have a different density, and that is why they have a different velocity. So if I have a different density and velocity, it means that I have a different acoustic impedance. And that is why, due to the change in this acoustic impedance, I am getting a reflection from all these layers. So if I will just increase this number of layers to n, then I should get n number of reflections, and all this energy get recorded with these receivers R1, R2, and R3. So this is what the theory and how it works. So for each different layer with different acoustic impedance, we have reflections, and these get reflected and have get recorded from this to these receivers. And also the second point to note here is that if the velocity is higher, it means the density is higher. So this ray will propagate faster when it enters the layer 3 with respect to layer 2, and slowest in layer 1. So it's a combined velocity of all 3 layers, which will govern how much time it will take and get recorded into this receiver R3. So that we have to keep in mind when we process this data and we do the interpretation, which is very important. And here is just an example which I show you in the very first slide, and now I think you will be able to guess a little bit that was the theory and how we are assuming things to be. So here we see that these rock layers are in different layers, and if we will see a close investigation, then you see that this rock layer particularly has a different material than this rock layer. So it means that it has a different material, it means it has a different density, and if it has a different density, it has a different velocity, and which at the end means it has different acoustic impedance. So I can assume that I will get a reflection from all these layers individually. So when I will process in data, I can investigate all these layers individually if I have a very accurate processing sequence, how to delineate all these different ones. So this is pretty much what the application of the seismic method into the exploration. So here I have just written that we can assume as an approximation that higher density is we can see that it's higher velocity, though there are some more parameters which govern that velocity is higher when the density is higher. In some cases, it's the opposite, like in salt domes, we have a lower density, but we have higher velocity. But I will not go deep into that. But pretty much it's valid for most of the cases. So now I will show you a bit of the application of the seismic in the Arctic environment or in the Antarctic. So pretty much what we have discussed is about the application of the seismic in the exploration, that is in the exploration of oil, gas, or minerals. Now I will tell you some research applications of this seismic method, how we can, with a different approach, we can use the same method for different investigations. So in this summer, we have in Svalbard, Spitsbergen, Norway, we have just did one seismic survey in which our objective was to find this basement layer. And to find this basement layer, indirectly we can say that we need to find out how much the ice layer is deposited before that. So in the first slide, what I called as the bedrock. So the basement layer is something which penetrates deep into the crust, and which we can see even in some cases up to the surface. So our target was to somehow map this ice layer, and if we will be able to accurately map this, how much the depth of this ice layer, then we can know that where is my basement. And it's important if we have to make some permanent structures or something in the Arctic, because the mining and exploration in Arctic and the Antarctic both were restricted. Nobody can mine there. So it only has up to now some research investigation. So, but if we have to build some research stations there in future, so we need to know where is this permanent basement layer, and for that we need to know this ice layer. So the thickness of this ice layer. So in the same manner, what we did is we put this geophones or the receivers on the surface, and we have our source just beside these survey lines, and we use this, and each time we were changing the position of this source along this line, and each time the energy is propagating through this ice layer. And because there is a acoustic impedance change, because the density of this ice layer and the basement layer are both different, so the energy will get reflected from here, and it will ultimately get received to our receivers. And that is how we did it. This year we are still in the line of processing it. We still don't have the results to show. So these are the picture from this summer, and if you look closely on this line, so these small black patches you can see here are all geophone receivers, which is, you can see that in a straight line, as I shown you in the previous one. And on the left you can see that is a movable source which we used. Is not of very much high energy, because we don't need a very large energy source, because our depth is very shallow, and also you can see that is snow structures and everything, so we cannot use very high source. So so this is what we did in this summer, and we recorded this data, and we are in the stage of processing it. So in the next, to have a close look on that, you can see that this box is contains our acquisition recording, which earlier I shown you in a big truck, but because it's a very small survey line and survey, so we can do it pretty much into a small scale. And here we can see that this is our energy source, which is giving power to this weight drop. It's same as the vibro size, so it is hammering into the ground with a plate which is permanent into this beside this seismic line, and we are just thumping this ground with this weight drop, and it is producing the energy. And there is this closer look of this receiver. You can see here and here. And if you I don't have a video recording to show you. And if you just see that this black black cylindrical thing here, it is the weight drop which is pumping this energy into the base plate. So it just lifts up and it just goes down very rapidly, so that it can just thump this base plate really hard, so that we can penetrate some energy through this loose ice which is on the surface, you can see. And there is another application of the same seismic method on monitoring of the calving of this ice. So calving of ice is when these big icebergs or glaciers, when they meet at this the seas. So there is the chunk of ice from these glaciers or icebergs, they get breaks and they fall into the sea. So what the earlier method or the still method is used, that the research team, they put a very high resolution camera at some distance from these positions, and what they do is they took some random, not random, sorry, it's high resolution photographs at fixed interval of time, let's say 15 minutes, and they try to investigate that how much this ice has break, and that is how they used to compute that how much ice has been lost into the summer or into the cold season. But that way you need to transport that data, and every time physically you have to verify it, and another way you don't have really a very accurate quantitative measurement that how much exactly you have lost. So how we can use the same seismic method that you can see here is just a drilling machine. We drilled into this hard ice and we put our geophone inside that, and we connected the geophone with this permanent structure. It contains the batteries and the acquisition system. We can put the batteries which will last for like 3 months into the extreme cold conditions as well. And the principle how it records is the geophones we have already planted into this hard rock. And what happens when this chunk of ice, when it breaks down from here and falls into this ice, so it creates some energy. So it's the same way when you throw a stone into the pond, you see that some circular rings get formed, because you throw the stone which energy which currently has a kinetic energy, and when you put it into the ground, it gets converted, and that is how this energy gets distributed into this whole lake, and we see this ring of waves. So the same thing happens here as well. When the large chunk of ice falls into the sea, then it creates this energy, and this energy gets propagates from this water body to this layer, and it ultimately gets propagate and it hits this geophone, which gets a recording. So the application of this is that you don't now need really physical verification. You don't have to visit there. You just need this equipment, and every time when some big ice chunks falls down, we always get a signal into our geophone, and we can just download this data and we can just process it. So it's in a digital form. We can pretty much process it, and we can have a very accurate quantitative measurement that how much we exactly lose, because we are very much now focused on this global warming and the rise of the sea level. So this is another example of that, and there is this just another picture on, so another seismic station which we put permanently covered with rocks, so that the polar bears cannot destroy it, and we just put some smileys or other indications just to know that after the cold season, when we are in the summer, we can know that exactly where it is using the GPS. So here you can just see that there is this glaciers and the iceberg, and we are permanently getting some chunk of ice falling off from this uh, structures, and every time we are getting some signal and we are recording it. Also, the second application of the same system, which is here, is the earthquake monitoring. So if we put this number of receivers at different places, then we can, if some earthquakes, some shallow earthquake of some very small intensity happens locally, then using these geophones, we always get a signal, and we can instantly compute how much is the intensity of that earthquake, and where it happened exactly using the geophysical method. But what our team right now is more focused on, not on the large scale earthquakes, because we already have many of the seismic monitoring stations all over the world. But what we are focusing right now in investigating about some small seismic events or earthquake events which is happening in the because of this is very big icebergs and glaciers. So we are trying to find out that does the ice is also behaving in the same manner how the rocks behaves, because when earthquake happens, when there is a huge accumulation of energy in the rocks, and when the overburden pressure is exceeds the threshold value, the rock just disrupts, and it releases a huge amount of energy, and this energy propagates through all the interior of the earth and reaches finally to the surface, and which we experience as an earthquake. So until the time something is accumulating, we call it a natural hazard. But when this hazard comes and destroys all the property, and we have a loss of life and property, we call it a disaster. So in the same way as the large scale earthquakes, we are also trying to find those that does the our huge glaciers and moving icebergs also creates this small seismic event. Are they also behaving in the same way as how our rocks uh, behave elastically? So this is under investigation, and we are using the same seismic instruments, which is the acquisition system, the power, and the geophones in particular. So what I will end now. This is pretty much what I have to say. And so what we have learned today is that what is the seismic method, what how we are using it, and what's the basic principle, and we have tried to figure out that what are the applications of this seismic method in the exploration, that is in the oil, gas, and mineral industry, and groundwater exploration as well, and also in the research activities as well. So thank you very much, and I hope you get this, and please let me know if you have any question into the chat box, and I will try to answer them. Thank you very much.